Okay, so let's start going over the Chapter 6 test objectives. However, now, for this video recording purposes, this is also going to be your what? This is your midterm as well. Okay, so for this video purposes, this is Chapter 6, but this will also be your midterm. So the first bullet, again, I'm just going to read the bullet, and then you can kind of catch up with us. So this is the first bullet on the test objectives. Know the definitions of chemical, ionic, covalent, and metallic bondings. Yes, right here. Okay. So I wrote these, and I know it looks like a lot, and it's not perfect word for word if you were to pull up Webster's dictionary, but it's as good as it's going to get, and it's as good as you need. The chemical definition is actually pretty spot on for what it needs to be. The key here is it focusing on one thing, or is it just talking about a broad definition? This one's just a broad definition of what is a chemical bond. Okay, that's what it's really meaning here. It is a mutual, and why does it have to be mutual? If one doesn't want it, you're not going to have a bond. It's a mutual attraction between one atom's nuclei. Okay, so that's like if I'm an atom and Tyler's an atom, it'd be like my nucleus and an adjacent. Keyword there is adjacent. What does adjacent mean? Near or around or close to. The atom's valence electrons and the other atom's valence orbital. Okay, does that make sense? So it's like my nuclei attracted to his orbital. Okay, so it's going to be that attraction. Now, there's three types of bonds. We've talked about this over and over again. What is an ionic bond? What is a covalent bond? And what is a metallic bond? The key here in ionic, what's the key word? Well, it's going to be a transfer of electrons through difference of charge, creating what two types of things? Cations and anions. What is the charge of a cation? Okay, this is going to be positive, and an anion is going to be negative. So you have a complete transfer of electrons there. Okay, covalent. What's your keyword there? Sharing of electrons through two non-metal substances. Again, so the keyword there is going to be some sort of equal sharing. However, do they always share equally? No, that's the key part that you should already know by now. And the metallic, the key part there is a sea of electrons are created by a network of overlapping orbitals. What does that sea of electrons allow them to do? Yeah, flow from one end to the other with nothing hesitating or nothing holding them back. Are some metals at better conducting heat and electricity than others? Yeah, you put aluminum foil in the oven. When you get it out, can you touch it? You can just grab it. But if you grab that pan, it's going to burn the mess out of you. So some can conduct others better than electricity and heat better than others. So that's
the other day, but I actually touched the pan.
Doesn't feel good at all. Yeah.
You said that, so I tried it. And then I was like, you lied to me, but I realized I touched something.
So you grabbed a hot pan because I told you.
No, it had aluminum foil on it.
You got to get the.
I grabbed it like this, so the thumb was
Ow.
aluminum foil and the
But the other finger didn't burn, did it?
No, it didn't.
No, all right. So at least I was right. I'm so glad that I caused a third degree burn because of something that I taught you. All right. Next, this is the next bullet. Understand what potential energy does as atoms bond and how it affects the stability. All right. So when atoms bond, this is kind of how it can start off. The bond length. What is the bond length? Okay, the distance between the two bonded atoms. Okay, forms where the potential energy is at its minimum. That's the key part right there. The potential energy is going to be at its minimum, and molecules are most stable. So that's the key part there. The potential energy is going to be at its minimum, and it's going to be most stable. Some of you may remember this, and I'm just going to kind of include it in. You don't have to go back and draw it, but you can if you want to. It was this chart, okay, and it was distance was the x, and y was the potential energy. Okay, and it kind of started off like this and went down and then went back up. And this was the point where they were too close. They overlapped too much. And then this was the point where they were perfect. They overlapped just enough. Do it. This is how the bond length, when it's perfect, the potential energy is at its minimum. And it's most stable. Okay? And the farther apart they get, what happens to the potential energy? It goes back up. And to the point where they're completely separated. So this was one of the charts that was on the PowerPoint. So again, When it's at its perfect bond length, the potential energy is at its lowest point, and this is where it's stable. So you're going to make a chemical bond there. That's okay. All right, I'm going to go ahead and read the next test objective, so whenever I get to that slide, you can know what we're talking about. The next one is know what types of elements bond in an ionic, covalent, and metallic. Hopefully you know this point already. Brittany, you good? Okay. All right. In an ionic, it's a metal and a non-metal. Let me help you out as far as the periodic table is concerned. What is that line called that's always dark and heavy? It's a blue on that, it's orange on that, and it's red over there. That separates the metalloid line. So if it's a metal and a non-metal, where do the metals come from? The metals are left of the line. Where are the non-metals? Right. There's one exception. What is that one exception? Very good. Except hydrogen. Okay. Hydrogen is the only non-metal left of that metalloid line. It's the only one. Okay. It's the only one. So what you're going to have is you're going to have cations. You're going to have anions. You're going to have cations, and it's also going to be polyatomics as well. All right, so covalent between two non-metals. So where do both of them have to come from? Very good. So both of them are right of that line, except hydrogen. So that's the one that can be to the left. So, okay, and metallic. They're two metals. So where are both of them going to come from? From the left. Okay, so both are from the left. Okay, or a pond or a lake or a river or a stream, whatever you want.
Oh wait, I didn't finish. A toilet bowl of electrons.
A toilet bowl of electrons.
It works. The body of water.
If you want to go that far. All right, the next bullet. Okay. Understand what polar and non-polar covalent bonds are, the differences, and what causes the differences. So here's that slide. Polar is an unequal sharing of electrons. Okay. What are these things that I have labeled that kind of like S's? Okay. You will see them on the test. I have them labeled as both partial and slightly charges. If you look it up in a book or online, they're going to be called partial charges. So you're going to have a partial positive and a partial negative. When you have two poles, what is that called? Very good. That one molecule, why do I keep writing P's? Okay. Okay. It's a dipole. All right. Non-polar is going to be equal sharing. So are any poles created? However, today we talked about this. We talked about how when an LDF, it's caused by all that sudden, that momentary shift in poles. Because if I have, most molecules are larger than this, but hydrogen has one electron. Will it always be 1 and 1? For a split second, it could be 2 and 0 on either side. So for that momentary split second, it can be different, but most of the time it's going to be that way. Yes, ma'am. Hang on one second. Okay. All right. So if I have nitrogen, this one has 5 valence electrons. That one has 5 valence electrons, right? Okay. So they're the same atom, so is either one any more electronegative than the other? No. So when we have this sharing of electrons, it's going to be equal. However, 100% of the time, will it always be 5 and 5? No. At one point, somehow, some way, there's going to be a shift. Okay? It can be 9 and 1. Because there's 10 total, right? So for that one split second, all 9 can be on this side and only 1 can be on that side. When that happens, are more electrons on the left? So that means it's going to be partially negative for that split momentary second. Now, the very next second, it can go from that to that. But is it still uneven? Yeah. So for that momentary split second, and then the very next second, it can go back to 5 and 5. Okay. On an average, it's equal. But for very few moments, they can be uneven, which create that high five effect. Okay.
Why do they shift electrons?
Because they're constantly moving. Okay. Will the halls always have the same amount of kids everywhere you go? No. They're constant. When people are constantly moving, things can shift around. Okay. All right. So that's kind of what that is all about. All right. So let's go to the next bullet. This is where I got to pick up starting writing. All right. Understand. Oh, I didn't talk about this. What causes the differences in polarity? What's this right here? Electronegativity. All right. So make sure you know what that stands for. All right. So next, understand partial and slight charges and how to identify them. Can I just answer this on this slide? Yeah. Where are the partial charges? The plus and minus, and that's how you identify them, right? When will you see them? Maybe I may make a point here. The partial charges, only on polar are they seen. Okay, you'll only label them on polar ones. Now, somebody asked me this question. When you see, is an ionic molecule a dipole? Okay, the answer to that is no, and here's why. Because what are these electrons being done with? They're being shared. In an ionic bond, what are they doing? They're completely given away. So, okay, here was the question. Is an ionic bond, such as, if I wrote that, how could you tell that's an ionic bond? Okay, that it's a metal and a non-metal, right? How do you know sodium's a metal? What side of the line is it on? Right. So there's one on the left, one on the right. So if they're different, it's ionic. Okay. So what the question was, is this a dipole? And the reason he thought that is because Na plus Cl minus. However, are those partial charges? No, they are complete charges. So something totally different. Means when it's shared back and forth unequally. That is literally given to that one. However, when you look at this one, it's shared back and forth. So the hydrogen still gets it sometimes. So it's not a complete, exactly. So the ionic is a little bit stronger than this one because it's literally completely 100% of the time given the other way. All right, we good there? So let's go to the next one. Know what a molecule and a molecular formula is. A molecule is a chemical substance held together by a covalent bond. The key there is it's held together by a covalent bond.
Joshua Scott, if you're in the building, please go to the gym. Joshua Scott, if you're in the building, please go to the gym. Thank you.
Okay. All right. So a molecule is a chemical substance held together by a covalent bond. The key there is it's a covalent bond. Okay. So what is a molecular formula? What does it have to represent if it's molecular?
Like it uses symbols and stuff.
Yeah, it's got to represent a molecule. However, what is it telling us? It uses the symbols and the subscripts. And what does the subscript tell us very explicitly? Very good. How many of each element there are? So in H2O, how do you know that this is a molecular formula in the very basic terminology? It must be a molecule. First of all, if it's a molecule, what is it held together by? Covalent bond. Okay? What is a covalent bond made up of? Two what? Two nonmetals. So what side of the periodic table are they on? The right side, except hydrogen. So is that a molecule? Yes. What did you say? Okay. Hydrogen's the exception. It's a non-metal.
It looked like a TI on your thing.
My bad. All right, so hydrogen is a non-metal. Oxygen's a non-metal. It's a covalent bond. So that's a molecular formula. Same thing with an H3. Same thing with CH4. What about CO2? Are both of those non-metals? Yes, both of them are non-metals. So that is another example. Without hydrogen, that would be a molecular formula. Okay? All right, next bullet. Know the definition of bond length and how to apply it. Okay? Bond length. That almost it? Okay. Bond length, the distance between two atoms bonded together.
I didn't understand what you meant by how we apply it. But I just couldn't-
Yeah, just know what the bond length means.
We didn't know it's measured in
Ah, yeah, that's a good point. Let's talk about that. Do what?
Jordan said, what's the point of being if you're on the phone and that's not So what's the reason?
All right, so let's talk about the next bullet. What is bond energy? This is the key to this in red. So what is bond energy? The energy required to break it. Not make it, not form it, not create it, not what's there. How much energy is required to, if I wanted to break those two things apart, how much energy I'd have to put in order to snap them apart? Okay, how much energy I would have to put in order to snap those two things apart? All right. Everybody good there? Let's talk about the next one. The next bullet is the definition of electronegativity. All right, the definition is
Are you going to ask us on the test what's the most electronegative?
potentially.
It's the biggest bully.
Okay. So electronegativity, ENEG, what is the definition? It's the chemical attraction of one atom to the valence electrons of another atom, and the key here is in a chemical bond. Okay? And what do I mean by that? When H is bonded to F. Okay? What I mean is how attracted is F's nuclei attracted to the valence electrons of H. Now, in this case, we've already said F is the what? Most electronegative. Therefore, how attracted would it be? Very attracted. So you're definitely going to get this thing going on. Okay? And again, I taught you the bully thing. Let's step up. Let's move on. Let's go ahead and let's use the chemistry terms, okay? So it's the most electronegative. So again, the key there is it's an attraction in chemical bond. Because I'm not talking about this. I'm not talking about how attracted is F to its own electrons. That is electron affinity. Okay, what does affinity mean? That's the love of its own electrons. Electronegativity is when it's in a what? In a chemical bond. That's the difference. Because somebody asked last time, what is the difference between affinity and electronegativity? Because they're kind of the same. Electronegativity is in a bond. Affinity is within an atom itself. It's how much do you love yourself. Okay? All right. The next bullet. Know what elements can potentially make double and triple bonds. And then it has a sub-bullet of compare double and triple bond strengths and length to single bonds. All right? So, there are only 3 elements that can make them. Okay? Does anybody know what those 3 are? What?
What did you say?
Boron. 3 elements. Nitrogen. And oxygen. Those are the only 3. Carbon, nitrogen, and oxygen.
They're the only double and triple bonds.
Those are the only 3 that can make double and triple bonds. And a normal, there are very few rare exceptions. But these are the ones you'll see most common. Okay, these are the ones you'll see most common. All right, so this is another little phrase. Which of the following is not? That makes sense?
Which of the following is not a double?
See, I never know how you're going to twist it.
Or which of the following is missing?
Wait, what? So it's going to be like...
Okay.
Blah, blah, and blah. It can be blah, blah, and blank can all form triple bonds. See what I'm saying?
Or you could say like
Or which of the following is not one that can form?
calcium, carbon, nitrogen.
Exactly.
You would say like which one of these doesn't
So it depends on how the question is worded. It can say blah, blah, and blah. Excuse me, blah, blah, and blank can make a triple bond. Or it can say which of the following cannot make a triple bond.
So it would be carbon, nitrogen, oxygen, and hydrogen, and you pick hydrogen.
Exactly. All right, so this is the little phrase, the shorter, the stronger. All right, and so this is kind of what I'm saying. The triple is the what? Remember how I got, Tyler, stand up here for a second. Okay,
When you got king.
okay, okay. What would this represent? Single bond. Is it easier or harder to break this? Easy. Shoulder, what will that? Okay, it's a double bond. What happened to the distance? It got shorter and it get harder to break? Yes, now if I gave him a big hug, what would that represent? The triple, and that will be even harder, right? So, in essence, the shorter, the stronger. Okay? So, in essence, what could you say? The triple is the shortest, so it is the
Hardest.
most energy required to break, therefore it is the strongest.
I was pulling for hardest
Why?
because if it's shorter, it's harder to break.
So, the single, guys, y'all please stop. Okay. The single is the longest, therefore it is the weakest. Thank you. So, shortest, strongest, longest, weakest. Okay, so that's what's going on there. And the middle one, the double bond, would be in between both of them, right? All right, we good there? Matthias, you got it? All right.
I'm confused on what you think we want to do.
You fill that blank in.
I'm sorry for yelling at you.
All right. Let's see the next bullet. Know how to recognize a correct diagram of a Lewis structure and the parts. Know why one element is the Lewis structure is the central atom. Now, the Lewis structure stuff we're going to do at the very end, so I'm going to hold off on that bullet, but I will tell you this. Okay, the one that's in the center has two available potential answers. What is the one we've always said? If carbon is present, it's always in the center. But why is that the case? Perfect. Most available bond locations. Because how many does it need? It needs 8. Well, carbon only has 4. So it's got 4 available bond locations. Okay? And there are some instances, some, not all. You know what? I don't even want to tell you to. It doesn't matter. Has to do with electronegativity, but doesn't even matter. So you just need to know number 1. Okay?
You said we're coming back to that.
Yeah, we'll come back to Lewis structures at the very end. Okay? Know how the chemical formula in an ionic compound is represented. What did I mean by this? The chemical formula in an ionic compound is represented. No, it's not. I just don't remember what I was trying to ask you here. Whoa, that's not what I wanted. Okay, so next bullet. Know how the chemical formula in an ionic compound is represented. Crystal is I think what I'm trying to get out of here. Okay. It's just a crystal. It forms a solid crystal. It's a crystal network. Essentially, the terminology is a crystal lattice. And okay, this is what it is. That was it. Smallest whole number ratio. That's the key to that. It is represented by the smallest whole number ratio. Because if I pour salt in your hand, is that just 1 Na and just 1 Cl? No, that's probably a billion or two that I've just poured in your hand. But are you going to write Na 1 billion and Cl 1 billion? No, you're not going to write that. You're going to write the smallest whole number ratio. So if I give you something like this, Na2O. If I give you 10 oxygens, how many sodiums would you have to have? How many? Why? It's for every 1 oxygen there are 2, so you double it. What if I gave you 40 sodiums? How many oxygens? 20, because it's half, right? That make sense? Okay. Every time I give you 2 sodiums, how many oxygens am I going to give you? 1. Every time I give you 10 sodiums, how many oxygens? 5. Every time I give you 20 sodiums, I'm going to give you 10. So it's always half. Or double. If I give you 100 oxygens, I give you how many sodiums?
Oh, no.
So oxygen,
200.
you double oxygen and
Half, yeah.
divide.
So it's just, bottom line, Laura, don't think too hard. It's the smallest whole number ratio. Bottom line. Okay? I mean, you could even go as far as this and say Al2O3. So every time I give you 2 aluminums, I give you how many oxygens? 3. So if I gave you 6 aluminums, how many oxygens? 9. Very good. Okay. How did I do that? Well, 2 times 3 is 6. Well, 3 times 3 is 9. Okay? That's okay. No, that's fine. I just wanted to show you smallest one ratio. All right, the next bullet. All right. Know the difference in physical properties of ionic and covalent compounds. Bottom line, ionic is the strongest. Okay? So it has high, not heat, has high. If I write MP and BP, we know what that means? Melting point and boiling point. Okay? High melting point and boiling point. Okay? So those are some things that you can have. So ionic is the strongest. It's got a high melting point and a high boiling point. If the solids are normally brittle, which means you can crush them, right? If it's covalent, it's the weakest. It's got low melting point, boiling points. Normally they're gases, but if it is a solid, it's a very fine powder. Okay, very, very, very fine powder. What's wrong? I did a GIF one time. It was a box full of hangers and went over very well. Yeah, it was good.
I've got to tell you what the best gift was.
Everybody good with this one?
And I gave someone my sister's organic book.
That is awesome. All right, the next one. Know the properties of metals. Okay. They conduct heat, and that's electricity. I know I miswrote that word. They conduct heat and electricity. It just looks funny. Malleable. Ductile. Luster. Okay. So the biggest one there is they conduct heat and electricity very well. What does malleable mean?
It's able to be beaten into a thin sheet.
Okay, thin sheet. Ductile,
Wires.
thin wire. Okay, luster is shiny. Is that right? Is there no E in there?
There's no
No, it's
That's
SH. That's shiny. Or
Sheeny?
shiny.
Is that sheeny? Now let's get rid of that E. Yep, that's exactly right. And then we know brittle. So again, that is the properties and characteristics of a metal. All right, the next bullet, just brittle. Like easily broken, yeah. Brittle, easily broken. All right. The next bullet we're going to skip, but I'm just going to tell you guys, there's nothing I can do for you on this one. You're going to have to put in the time of the Vesper information sheet, the one that's got the model type, the AB model, the geometric shape. What's wrong?
There's nothing we can do for that, and that takes up half of it.
That whole sheet is all the information. There's no reason to rewrite it. You rewrote it, so you studied as you wrote it. So, that's how people are kinesthetic learners. When you write, you learn. That's how some people learn. There's 4 different types of learners. There's kinesthetic, there's auditory, there's visual,
Well, it's writing and learning.
kinesthetic.
That's what I mean.
If you can listen and learn, you're auditory. If you're visual, you have to see it.
I've used all of them at least 6 times.
All right. So again, bond angle, hybridization, polarity, IMFs, all those things are on that sheet. You're going to have to look those up. Okay, again, I'm going to work any of those Lewis structures you want me to work at the end, so I want to cover everything else. Okay, the next definition, or the next bullet is know the definition of hybridization. What?
Best burger, is that good?
Is chicken salad chicken good? It's the best.
Chicken salad chicken, do you like chicken salad?
I didn't like
I don't like chicken salad. But I was wondering what I was.
Alright, I think I wrote down the wrong definition of hybridization.
Is that open yet?
Or, yes.
I'm highly disappointed that.
That sits beside me, she works there.
Okay. I'm highly disappointed that Richie B's closed. That devastated me. That broke my heart when I saw that.
Yeah, but that's
Yeah, my chemistry, my last
Is it?
chemistry grade broke my heart.
Because he was him. He was the original Conan the Barbarian in the original movie. That was him. All those posters in there, that was him.
Wait, really?
I don't even know who that is. I don't either.
It was an old cartoon, but it was a movie that turned into a cartoon.
Yeah, he was in that movie.
Yeah, he was the original Conan the Barbarian. Why am I? Okay, so hybridization, the sharing of electrons. The key here, and I should have done this in red, overlapping orbitals. Okay, that's the key there. Is that for you to have hybridization? And guys, I'm going to be honest with you. The chemistry behind this is very complicated, very complex, very detailed. There is no reason for you to learn the chemistry of it. You need to know the definition and how to calculate it. But how do you calculate it? You count. If you can't count, then you don't need to be at school anyways, okay? So the ease of calculating it is very simple. But the complexity behind the chemistry of when you have two atoms and their orbitals overlap that's way up here, okay? I don't even know if I could explain it, okay? It's very difficult. Yes. Yeah. Yep. Okay. All right, yeah, very simple. So the next one, know what IMFs are and what they affect. Know IMF strength as compared to ionic and covalent bonds. All right, so what is an IMF? All right, so an IMF is an intermolecular force. All right, so what is an intermolecular force?
Forces of attraction between molecules.
Very well done.
Well, he already did it.
No, I studied it.
I was like, no.
Forces of attraction. The key word here is between molecules. Now, one other little key fact here. A molecule is what?
Oh, I have this.
Covalent bonds. Very good. Okay. So, I gave you this sheet right here, the one that has IMFs. And I called it a BART earlier, and it didn't make sense. It was a box and a chart, so it was a BART. The only places that you have IMFs in this little chart, you can look at it. It's right there in front of you. It says intraparticular, ionic, metallic, covalent, and then it says intermolecular. Ionic, there are none. Metallic, there are none. Covalent, it lists all three. So covalent is the only place you have IMFs. Yes, sir. Pass that back, please. Lowell, I think you need one as well.
On the thing it says no IMF strength.
All right, yeah, I'm getting there. Okay.
So
All right.
Since you just wrote covalent bonds, can we just say only?
Yes, only in covalent ones. Do you need one too? Okay. All right. Now, so the streets. So IMFs are weaker than bonds. And what are the three bond types?
Ionic.
Ionic, covalent, metallic. So these are weaker than bonds. Okay, these are weaker than bonds. And again, if you want to add those in, you are more than welcome. Ionic, covalent, and metallic. Okay? They're weaker than bonds. So here's what I'm trying to tell you, is that, where are those molecules? The stick figure ones.
No, they aren't.
Here they are. They're on the wrong side. All right. A bond holds this together. A bond holds this together. But a force holds them together. It is easier to break that force than it is to snap this thing apart. Does that make sense?
Is that what me and you were
Hang on, guys. What? Okay.
Is that what you were doing?
Kinda. All right. The next one. Know what a dipole is, how they're created, and from what types of bonds they form. All right. So a dipole. Okay. So a dipole is created from an uneven distribution of electrons in polar molecules. So what does dipole stand for? A dipole stands for two poles. Okay? Know what a dipole is, how they're created, and from what type of bonds. Have I answered all three of those questions?
Wait, what question?
Polar molecules, which is covalent bonds.
How do we know, like, I didn't know that.
All right. We have ionic, metallic, and covalent, right? Covalent has two types, polar and nonpolar. Okay? So, when you see a dipole, what way does the arrow point? What way does it point?
Towards the negative one?
What negative? The more electronegative, because it is negative, right? So what way is it pointing in this one? And I did that for a reason, because it's not always going to be to the right. Okay? So in this case, it's going to point this way. The tail is going to look like a positive, so this one's going to be slightly negative, and this. It doesn't necessarily have to point to the right. It's going to point to the more electronegative one. In this case, it is chlorine. And that's why I did it backwards like that. Okay? Because right and left will get you in big trouble. It's always going towards something, and there's a reason why it's going towards that something, and it's always more electronegative.
It's more electronegative because it's closer to fluorine.
Perfect. That's exactly right. Okay? So, what is a dipole-dipole IMF? It's when two of these do what? Form a connection. All right? So, if I have HCl, nope, that's not going to be right. Let's flip this around. All right? So, we have HCl. So it's when these two things form a connection, because HCl is a dipole, HCl is a dipole, and it is that force that connects them together for that split moment second. Okay. Do you agree that that chlorine right here is slightly negative? It's more electronegative, and the arrow is pointing towards it. Correct? How do I know?
Because it's closer to fluorine.
Essentially. Okay? Down here. Agreed? All right. This chlorine is slightly negative, right? All right. So if that chlorine's slightly negative, then what is this one? So what does that make hydrogen? What do positives and negatives do? Attract. That attraction comes in right there. No, you won't have to draw any of that stuff. No. I just need you to know of how they're formed. It's when...
How would you ask that? Like,
Just know what a dipole is.
no, how am I supposed to ask that?
I agree with that.
Big word. I agree. Because he wants us on.
Dipole is the-
Whoa, that's not what I need.
Left, big word, right. Oh, big
That's your fault.
word like,
Oh, you've never passed the test. What about the polyatomic? That's
Yeah,
easy.
like 5.
All right. We have two more bullets. Know what hydrogen bonds are and what special ways they form. Fawn and to the unshared pairs of electrons to the electronegative. All right, so what are hydrogen bonds?
They're the weakest. Strongest. They're the strongest.
What?
Yeah, I was.
All right, so this is what you need to know. Between hydrogen and the, let me change color so you'll know it's important. You'll smoke it in college if you have to take it. I promise. Yep. Where'd he go? Because he has a professor he can't understand. Organic is a devil. That's why. Here's why organic is the devil to me. Normally, organic is in two different classes. It's organic 1, organic 2. That's normally in a fall semester and a spring semester. That's two 16-week classes. Okay, I took those two classes in one 10-week summer. So one 16-week class was crammed into 5 weeks, and I taught it to myself. And I made an A in the first one, B in the second one. So I studied 8 hours a day for that class. All summer. All summer long. Oh, it was the worst summer of my life. But that would have been the summer of 2009.
Do you always want to be a teacher?
Mm-hmm. Ever since kindergarten. I wanted to be a principal until I got into education. And I was like, that's a terrible idea. Just being honest. All right, so hydrogen bonding. It is the strongest. Matter of fact, please edit this. It is the strongest IMF. Hey, guys, make a note, please. It is the strongest IMF. And it's between a hydrogen, and here's the key part, of the unshared electron pair of a nearby fluorine, oxygen, or nitrogen. Okay, so what is that telling me? Let's look at water for just a second. We know that water has a structure that looks like this. Okay, first of all, if I asked you the shape of that, what would you say? Okay, that is bent. Okay, if I take this molecule, how many lines are drawn on the board? 2, so how many lines have to be on this? Okay, so do you agree that that kind of looks bent? Okay, that is bent.
107?
105. Okay, 105.
What's 105.9?
109.5 is tetrahedral.
7. What's 7?
Trigonal pyramidal.
What's 98?
Degrees? The boy band? I don't know.
No, I meant like...
There's no such thing as 98. I mean, all right. So what if I have another water molecule that's floating by? Okay. First and foremost, let's go back and read the definition. Hydrogen bonding is that a bond between the H and the unshared electron pair of a nearby. So if I look at this, of the nearby what? In this case, oxygen. Where are the unshared pair on oxygen? There and there, right? Those are the unshared pair. So the attraction comes from the hydrogen and those unshared pair. So it is going to be right there. That is the hydrogen bond. It's between the unshared pair of the oxygen and the hydrogen. So if I drew another water molecule over here, it's an H. It's a sideways H. Sorry. Yeah, let me rewrite that so it looks like an H and not an I. Is that better? Okay. Sorry. I did the H crooked. All right. So if I have this, where is the hydrogen bond going to occur now?
They're right.
Okay. between this and that, which is the electron pair. So I've got a hydrogen bond occurring right there. All right. So again, that is what it is. You good? Okay, where's the confusion? Okay, that's how a hydrogen bond is represented by 3 little dots. Instead of it being a line, because a line represents a bond. The dots represent a force. Always 3 dots. There's not anything going back and forth. It's just a attractive force.
Showing how it's moving?
All right.
Never mind.
No. I want to make this clear. IMF stand for intermolecular forces. All right. In a force, no electrons move. And here's why. What are the signs of electrons? Negative. So if this is negative, hydrogen is going to be slightly positive. For just a split second, it's like 2 magnets sticking together. So it's more of attractive. They stick versus giving back and forth.
So will we have to like draw this?
No. I'm just trying to show you what it is. You will not have to draw it.
Is it gonna be on this?
You have to know what a hydrogen bond is, but not the drawing. Okay. That's why they don't put lines, is because lines means electrons are moving. The dots just means it's kind of stuck together like a magnet. Okay?
So it's like it connects.
Exactly. It's where they're connected. But there's nothing going back and forth. It's just a magnet. All right. The last bullet, know what a London dispersion force is and from what types of bonds. So an LDF comes from what 2 things? I don't know.
Intermolecular and London dispersion.
London is like, if you think of a diamond in London.
Fritz London was the guy.
Well, I'm saying, like, this is how I remember it. Like, London is like the weakest. If you think of a guy named London, that sounds like a weak person. So,
A way that I kind of taught it my first year, the noble gases can have these. All right, London, what is it ran by?
energy.
The queen. The queen is of nobility, and so nobility, London,
Non-polar.
whatever. Okay,
Hybridization.
Hey, there's Coach Bright.
B/T. B/T.
between.
2.
Okay, all right. Now that is it of test objectives. Are there any Lewis structure things you want me to cover? Anything at all? You tell me. You tell me, and I'll teach it. I'm not gonna do all of them.
They're so hard.
You missed one day, and it has just shattered your world.
Yeah, that is what happened to him. I mean, no lie, that is exactly what happened.
got 3.
That Vesper info sheet.
That's what she would.
I'm talking. I needed what Lewis structure?
Like give her like H2O.
Will it be illegal if I take a picture of this?
Why?
You already have one.
You look one up at home.
How we have to draw it?
All right. The way it's going to be listed on the test is I'm going to give you one of these. Matter of fact, there's 5 drawings you have to make. Okay. So I'm just going to pick the first one. This one is not on there, but it's going to say number 1, and it's going to say CF4. This is just number 1 on this page. Okay. What you're going to have to do is it's going to have things listed. Number 1 is it's going to say the shape. Number 2 is just going to say the bond. Now, I may do these out of order, but overall, it's what all is going to be there. Number 3 is going to be the hybridization. Okay, number 4 is going to be the polarity. And number 5 is going to be the IMF between 2 of them. And then it's going to say draw it. Okay? So that's exactly what it's going to look like. Just like that. No, polyatomics is not tomorrow. No polyatomic tomorrow.
Not till next year.
Yeah, it won't be until next semester when you get back from Christmas. Now, here's the thing, Montana. We still have tomorrow to cover all of this. 6 period's the one that needs this. Okay? Now, Harrison, I have the key worked out to all of this. I'm emailing this to y'all tonight. Okay? work it on your own to see if you can figure it out first. Because if you copy it down, you won't know anything to do.
Well, I mean, I know
That's like copying people.
And if you want to come in the morning, I'll be glad to sit down and work with you.
I can't read max out.
That's okay. All right. So I hope this video has been beneficial, guys.
What do you mean?
Good luck on all your midterms.